Do you have any charger for this laptop?
Yes.
Yes, it's on here. I don't have the button there.
And Dr. Kabi, looks like I have to open the software from the beginning based on what he said. You know,
Yeah, yeah. As soon as you open TeamViewer, is there any way I can look at the screen from your camera? on your
Okay.
computer?
Yes.
Yes. Open the
Yes, I
WebEx
will-
team.
Yes, I will
Microsoft Team.
share my screen. Share screen.
Yeah, that's correct. No. You need to minimize the window. Now maximize this one. Now go to no. Keep this one. Go to this.
I want to share my entire screen. Okay. All right. Now, if I go back to, can you?
Now open.
Okay, so yeah, minimize this.
All right.
Let's get back to the desktop.
Okay. Let me minimize this. So I had this already open. So
right now they have it.
I minimize this, right?
Yep.
Yeah, these are the results from the previous experiment.
Right.
Okay.
So the TeamViewer icon right there on the left, just double click on that. Up. There you go. It's the third from the top. There you go.
Team viewer. Team viewer.
All right, there you go. Just leave that screen on for me.
Oops.
Oh. Okay. Now I have control of your computer here.
Oh, okay, cool.
Okay, that way I can click around so you guys don't have to. Okay.
Yep.
Get rid of this. Okay, so let's take a look at our data. So you can see here, this was the last shot that was taken. So the shot is when the laser flashes the sample and is read by the detector, right? So the red line is our pulse. That's the laser pulse that pops up, or that's when you hear the pop in the bottom section of the instrument. And then the black line is the rise measured by the detector. So it hits the bottom of the sample. There's a gradual increase, right, in temperature, and the detector reads that. And then as it goes through the sample, it dissipates from the sample, and that's when you see your kind of decline here, right? For diffusivity, it looks for the half height or the half time of the peak. So it's not quite half the height, but the amount of time it takes to get to the peak, it takes half of that time. So it's like right here or something like that, and calculates a diffusivity number. So over here you can see some. I think we went through a little bit of this yesterday, but not yesterday, but last week, whenever we ran these tests.
I'm sorry. Could you please let us know what is the reason for this jump in voltage, in volt? So I mean, what happened at
well,
that?
that's what I just went through. So what happens is the red line here is the pulse. Here, let's open this up all the way. The red line is the pulse, right? That is when the laser fires at the sample. Okay. The black line is what the detector above the sample is reading. So if you think about it, if you look at your instrument, on the bottom is the laser electronics.
Mhm.
Okay. In the middle there is the furnace, and at the top, that silver box, that's your detector. So what happens is the laser fires at the sample,
Yes.
it heats the sample up, and
Uh-huh.
it's measured how quickly it runs through the sample from the detector at the top. So it reads the temperature of the sample. So your furnace puts the whole, or your furnace puts the sample at a temperature that you want to measure it at, right? The laser increases that temperature by a degree or two,
Yeah.
right? And the detector reads how quickly that heat transfers through the sample. And that's what that black line is. That makes sense?
Yes,
Yes.
thank you.
Okay. So the idea here is we want to see the diffusivity number is how quickly does heat transfer through this material. In this case, we're running stainless steel. So that's what our voltage is. This is kind of just an arbitrary thing. It's not a value that's entered into the equation.
Mhm.
All of the diffusivity. The main thing with this is getting the half time of the peak, right? So at its peak, take half of the time it takes to get to that peak. So it's like something like this, and that is used in the diffusivity equation. Okay. So this number doesn't matter at all. The voltage doesn't matter at all for the diffusivity number. It's mainly just looking at the time.
Yes.
Okay.
Okay.
And this was shot 3. So let me tell you about so this is a specific number. This is segment 2. So 002. That's the first 3 digits are your segment. So we had 2 segments set up for this test. I think it was 50 and 100, right? Degrees for the temperature points. So this is the second temperature.
Yes.
This is the second set of numbers here, 0, 1. This is the sample. So you can have up to 4 samples in there. There's the carousel that holds 4 samples, right?
Yes.
Okay.
Yeah.
This was the first sample. We only ran 1 sample. So this is segment 2,
Inside that.
sample 1, and then the last 3 numbers are the shots. And we took 3 shots from what we set up, and this is the 3rd shot that we're looking at.
Yeah. It's
Okay.
the run. Number of run.
Sorry?
Is number of run. Test run.
It's number of shots. So there's 3 numbers here.
Uh-huh.
The first 3 numbers refers to the temperature point, right? So I mean, it's a DLF 1200, so you could have 12 temperature points. So if it was your 12th temperature point, it would be 0, 1, 2.
Okay.
Okay. The second set of numbers here, these 2 numbers, is your sample. So this can go from 0 to 1, or 1 to 4, basically 0, 1, 0, 2, 0, 3, or 0, 4. We only had one. Go away. We want to keep this. Go away. So we only had 1 sample loaded, so it's always going to be 1 for this. And then again, the last 3 numbers are your shots for the second temperature point and the first sample. Okay. It's just a naming convention it's good to know. Okay. All right, let's minimize or get rid of this. Once everything is run, it puts the software puts everything into a nice text file. You can open outside of the software if you want to, but if you want to open it in the software, we can go up to post analysis, select the results file.
Yeah.
This should take us to the folder. So this is our regular data path. Okay. And this was install. You can tell it here. So remember when we set up the test, the file ID field when you're setting up the test, that dictates your folder name. So we named it install for this one, and you can come into the results. And SST, the RST, this notation right here means results. So we can open this, and it gives us the results for our test. So
Yes.
again, we have our segment and our temperature, the average diffusivity for the 3 shots that were taken. So these 3 shots, it was shot 3 times. It's pretty consistent, and it takes the average of those shots and gives you the average here for each temperature segment. Does that make sense?
Yes.
I have a question. So
Okay.
in the previous experiment, our set point temperature was 50 and 100.
Mhm.
So why in the final results, so it shows the values for thermal conductivity based on 48 and 98. I mean, is close to 50.
This was the specimen temperature at the time. So there's 2. If you look at the front of your instrument, right? There are 2 temperatures, one for furnace, one for sample, correct, or specimen.
Yes.
Right. The furnace is controlled through the furnace thermocouple. That is for heating rate purposes. If it's controlled through the sample temperature, it would be all kinds of, it would be very difficult to, almost impossible to hold that temperature at a good temperature. Hold the temperature. So what happens is, as the test is running, you'll see. Well, I wonder if it's here. Let me show you. There's usually you can't see it here because it's finished, but there's usually a countdown. If I think it's 500 seconds, the sample temperature can't move 1 degree within 500 seconds. Once it meets that requirement, it'll try to maintain that temperature and then start taking the shots. Now, it can take up to like 2 minutes or so, depending on how many shots you're taking and how many samples you have loaded in, right? To get through all of the shots. So if you have like, I don't know, if you have all 4 sample holders filled, it could take up to 5-6 minutes, right, to get all the shots taken.
Yes.
And the temperature could drop a degree there. This is very normal for DLF testing.
So the temperature reported in the final results, I want to know that. I know the sample temperature and the furnace temperature are very close. But
Yes.
I want to know that this is exactly sample temperature or furnace temperature.
This is sample temperature.
Sample temperature. Okay.
Yes. Okay. So as I said, this results file. So if you don't want to open it through the software, you can just open it in the notepad, and that might make it easier to export if you want to do it that way. So if we let's get into the TA DLF data. This is our folder. Here's our results. Oh, well, it already kind of shows up as a. Well, you don't have it, but it's fine. But yeah, if you open this, you can open it. Select the program. Oh, that didn't work. I guess you can open it here too. I don't know if it's actually going to open. Have notepad? Doesn't look like it, huh? There it is. Oops. Oh, this is Windows 7. Okay. What? I guess that's, I'm not allowed to use this application for some reason. All right, we can just do it like this though. There you go. So you can open this outside of the software if you want to do it that way too. Okay.
Okay.
There's some more good information in here. So if this is not enough information for you, there are a couple other things that you can take a look at. If we go to display shot CDV values, there's a lot of good information in here. Again, we can select our folder. And now instead of going to the results section, we can go to SST. And this shows us our shots, our individual shots. Right, so you can see this would be the first temperature segment at 50 degrees, first, second, and third shot, and then our second temperature segment, first, second, and third shot. So we can open up and look at the numbers individually for each shot if you wanted to go that way. And there are a few different types of analysis that you can do. Our software, when it runs a diffusivity measurement, it will always display the Clark and Taylor diffusivity number. So there's a specific formula for that. Okay. And it shows you the goodness of fit for that formula based on the diffusivity numbers. Okay. So if you have somebody that's looking for a specific, Clark and Taylor is the most commonly used one, but you might have somebody that's asking for the Parker, or there's a couple of other ones. Just know that there are different. The software does do the calculation for different formulas, but the results section displays the Clark and Taylor as default. Okay. You can also look at.
So these are experimental correlation for what? These names.
It's the diffusivity formula. There are several. Clark and Taylor is the most commonly used and the one that we display here, but there are other ones. So we have some. I don't know if you guys are going to be doing customer samples, but some customers ask for specific formulas. Like, I don't care about Clark and Taylor. I want to see Parker. And the software does do those calculations, but in the results file, it only displays the Clark and Taylor. Okay?
Yeah. Yes.
So you notice here that only the last shot is displayed. You can look at all of the shots individually if you want to. Go up to post analysis, say select shots. And again, we'll get into our folder, SST, and here are all of our shots. So we can say open all of these. And I'll show you the difference between a good shot and a bad shot, because we had some bad shots, right, on the first test. That's what we were having some issues there. So, and you can see again here how the sample absorbs the energy, raising the temperature, and then it slowly dissipates that heat. Now, something like a lower thermal resistance sample would, you might see it dissipate the heat quicker. This is over 10 seconds. We never really looked that long. But yeah, this is normal for stainless. And this was our last shot, right? This was the third shot at 100 degrees. Here's our second shot at 100 degrees. So if you're having issues at one point or another, it might be good to look at the shots individually to see what could be the cause, right? What's happening? Why is it not giving me a diffusivity number? Could be that some of the energy is being blocked, or we have a little bit of shine through. And I'm going to hold this shot here, and I'm going to open one of the shots from the first test that we ran. Let's open that. That was this one. So you can see there's a big difference here.
Mhm.
Not working. Okay, so here you can see that there. It looks like this is what we call shine through, right? Some of the energy from the laser hits the detector without hitting the sample. Okay, we want to see the rise start at the baseline. So this is the baseline. This is before the shot. After the shot happens, we have some energy going straight to the detector. So the magnitude is so great that it doesn't really show up on the graph, right?
So, what are the reasons this happened? For example, the reason is for the because of sample preparation, is because of sample material. What is the reason for that?
Yes, that sample preparation is usually the number one cause. So for sample prep, your samples need to be opaque, right? So no light can go through your sample for them to work in this instrument. The graphite spray can get you some of the way there, but if you're using some sort of glass, you might have to sputter coat it with a highly conductive material like gold or silver. That, you know, and then coat it with graphite spray to fix that problem. I don't know what kind of samples are you guys going to be running. Oh, that's right. It was like a foam material, right?
Uh, so actually, we need to conduct the test for different materials. I want to ask you specifically about the materials. For example, one of the materials we are using is phase change material, PCMs. For example, let's say paraffin wax. Now we have a couple of challenges. For example, paraffin wax is gonna change its phase from solid to liquid during this process after laser is engaged and heat, so temperature is gonna up. So in this case, we have a phase change process. So this is one of the questions we have. And then, in order to improve the properties of paraffin wax, we need to add some additives to that. So those additives acting like some impurities in the sample. So that's another question, if how it can affect the results.
Yeah, so I'm gonna refer you to we have a TPP applications group. Those questions would be better with that group. They'll be able to help you with your, you know, that sort of thing. The service group is I'm used to looking at materials like stainless steel and molybdenum, stuff that we use to verify the instruments. The applications group will be able to help you with specific materials,
Yes.
and give you some advice on those. Okay, I can. I think I'll verify.
Yeah,
I'll verify
example,
the.
another question we have. So if you wanna use a liquid sample, how is the sample preparation? Because in this case, we
Yeah,
cannot use graphite.
Yeah,
How is
liquid
it?
samples. There needs to be a specific holder for that. You guys, it doesn't look like it doesn't look like you have that. Because
Yeah,
if
we don't have
you
it.
can't load a liquid sample into the sample holders that you have now. It would just fall right onto the laser optics. right? There's no bottom to the sample holders that you have.
Exactly. There is no container.
We'll get you in touch with the applications folks. They'll be able to help you out with getting the necessary tools to do that.
Yeah. So Josh, can you hear me?
Yep.
Yeah. So we understand we don't have the sample holder for the liquid samples. So let's say if we get those, we can directly load those to the in the same procedure for the solid sample.
So I've only seen the liquid sample holder one time, and to my knowledge, it's a capsule, right? Where you load the liquid in, but the same rules apply. You need to be able to absorb as much of the energy from the laser as possible. So it needs to be a dark surface, so the capsule would need to be painted, and it would need to be a very low thermally resistant, high diffusivity material to get as much of that energy through the sample as possible, right? And again, the applications folks will be able to help you with sample prep as far as the liquid samples go.
Okay. All right. Thanks.
Okay. So back to just normal sample prep. We did coat this sample with graphite spray. The reason for that is to absorb, right? To absorb all of the light that we can from the laser. Okay, and if you have maybe a spot on there that's not coated, for example, with the stainless steel, it's a shiny surface, so it would bounce some of that light back, and it would not be absorbed by the sample. So if you see yourself not getting a good shot, it might be because it's not absorbing enough light, or too much light is going around the sample, and you end up with something like you see here, where it's stepped up. The actual rise doesn't happen until after the baseline. It's stepped up a little bit. So just be conscious of that. If you're running a test and it's not finishing for some reason, or it's not giving you a good diffusivity value, you might have a sample prep problem. And remember that they need to be opaque and painted with that graphite spray to absorb as much of the light as possible.
Yes.
Okay.
Yeah. So Josh, back to what you mentioned before. You said some sample we need to coat it with some conductive material like gold. So can you clarify on what kind of sample we do that?
Well, I was just working with a customer recently who was working with a glass sample, right? So glass is it's see-through. So if you shoot that, if you put it in there and take a couple shots at it, you're not going to see this what we see here. You'll just see a baseline, and then straight up. This you see how this black line comes straight up here.
Yes.
You'll see just that, and none of this. This graph will not be here.
Yeah, because it's not able to absorb a laser energy.
Exactly. So if you have glass, you'll see that, and you can coat that. You can try and coat that with graphite spray, but that could not adhere nicely to something that's very smooth like glass. It might need a porous surface to get to adhere to. But and in that case, they have the applications folks usually recommend to sputter coat with some sort of highly, a high diffusivity material, and then coat with graphite spray to absorb the light coming in.
Okay.
But yeah.
So when you have sputtered the gold, how do you kind of subtract that diffusivity from? I mean, I guess how do you consider?
Right. How does that turn it, or affect your diffusivity value? I'll let applications go through that with you. They have more experience sputter coating and running sputter coated samples than I do. Again, for the service group, we look at the reference pieces that we send. That those are typically the only samples that we run, just to make sure that your instrument is working properly and it's not a sample prep problem. So we look at stainless, we look at molybdenum, we have copper. There's a thermographite sample, but those are the ones that we're usually running here.
Okay. Yeah. Thanks for that.
So that's kind of it for analysis of your data. It kind of rolls everything into a nice little file that you can look at. Let's look here. Data, install, results. If you open up your file, it shows you the individual shot values, the temperature at which the shots were taken, and then the average of those shots.
All the time.
Yeah. By default is this technique to measure.
And then if you're looking for specific things, you can take a look at the shot values themselves, or you can look at the shots themselves to see if you might have a sample prep problem or something like that. Okay. You can also go. So we looked at the shot CDV values. You can also do. Let's see. I think you can look at these as the results section too. No, you can't. So you have to look at the shots individually. This gives you, the CDV gives you more information. But some of this is not useful. Actually, yeah, this is nice. So it gives you the maximum rise, and then it should give you the time as well. Pulse width. But a lot of this stuff you're not ever going to need, but it's here if you do need it, right? If you're looking for a different conductivity formula to use. But like I said, most people are okay with Clark and Taylor. That's the one we report on our results file. But the other ones are here if you need them. Do you have any questions about getting to these files or setting up runs?
Yeah, I don't know how to set up run. Because can we go over that, please?
Sure.
You can run it.
Yeah.
So one thing to remember about this software is after every test, you need to restart the software before you start a new one.
You said machine can take all the way to 4 samples, right? So is there any label there to know which
sequence? I will show you that.
When you set up the test, it'll show you 1 through 4, and you can set the different names for those samples.
Yes.
Okay. We open the software. Operation. Start. Oh, let's actually, before I do this, you don't have this. Okay. What I'm going to do is I'm going to put the getting started guide on this computer for you.
Yes.
This goes through all of the, here, I have to do this on my end on TeamViewer. But I will get you the getting started guide. I think that would be very good for you guys.
Great.
Because it goes through how to set up a test, how to look at the data, that sort of thing. Because I know it's difficult to remember, especially if if you're not going to run a test for a couple of weeks. Trying to find the file on my computer. Give me 1 minute. Okay. Should be able to send this through TeamViewer and just put it right on your desktop here.
Cool. Yeah, we got it here. Thank you.
So if we open this up, it should give us it gives you things that should be taken into consideration before you start. And then power on, shut down. Preparing samples, this is good. It talks about sample dimension. That's very important when you're working with these transparent and translucent materials. Remember, we talked about that. So, and also reflective samples, applying graphite spray. So here's a little. This is good for you guys. So 1 through 4, it goes from inside to outside. So closest to the chamber is 1, and then you count out from there.
Yeah.
Preparing the instrument. So evacuating the chamber. Are you guys familiar with that? We went through that, the other day. So you need to evacuate, then backfill. So here it gives you should be under 100 millitorr. Then you backfill with your, I think you have nitrogen connected, correct?
Yeah.
You backfill with your nitrogen until you're back up to atmosphere. Talks about filling with liquid nitrogen, the detector. That's very important. And again, you need to have it set there for, I like to do 15 minutes, but by the time you fill your detector with liquid nitrogen, then set up your test. And if you have a high enough temperature, like 200 or something like that, the detector will be at a point where it's fine to run. So typically, the first thing you do is fill your detector, and then you can start your process. And then here's your setting up an experiment instructions. Startup information in here. So this is for a 1600, which has a 6-position carousel, but it's very similar to what you guys have.
Okay.
So operation, startup. It asks you the configuration. We have a 4-position configuration. We're just going to say no for now. And then you have, it has the label here for 1 through 4. Okay.
Yeah.
Let me find the email address for the applications group.
Yeah.
And I'm just going to write it in the notepad right here on your computer. I couldn't open it. That's right. I couldn't move it. Where was it? So there's your email address for later. Those guys will be able to help you with your sample questions, sample prep questions, and then liquid cell prep as well. Okay.
Josh, I have one more question.
Okay.
My question is that so for this machine, is there any sample weight consideration to ensure accurate measurement
Say
or
that
not?
again.
So for this machine, is there any sample weight?
Oh, weight.
Sample consideration, yes.
So
accurate-
density is a big consideration, especially when you're running conductivity tests. It's required along with the specific heat of the sample, and there's a section in here on running maintenance. Yeah, so if you're running conductivity tests, which are you guys looking for a conductivity, or you're just looking for diffusivity?
Yes.
So when you set up a diffusivity run, or sorry, a conductivity run, startup information. So, and you can make that distinction here where it says specific heat conductivity. Let's the way you do this is if you have an unknown material, right? You don't know what the conductivity is. You need to have a reference piece with the same, or not the same, but similar specific heat as your material, your unknown material. Okay. You guys have stainless steel as a reference piece. I don't know. I doubt that that's very close to the material that you're going to be running.
Now the question is that when thermal conductivity of unknown material to us is unknown, so how we can figure out a similar material with the, similar conductivity with unknown materials?
I think this would be another good question for the applications group. We have instrumentation that can do that. I don't know. Maybe they have the information that you're looking for, as far as the specific heat. But yeah, the applications group might be able to help you out a little bit better than me in this situation.
Yeah. So based on the experience you have for this machine, could you let me know if the machine is able to measure conductivity of mixed materials, not just pure material?
Well, so the thing is like you can actually set up your own standard, but it's going to give you a number, right?
Yes,
and
definitely.
This instrument measures diffusivity directly. Conductivity is indirect, right? The diffusivity number is plugged into the conductivity equation with the specific heat and the density to get conductivity.
Exactly.
Right.
So the machine first measures, experimentally measures thermal diffusivity, and then thermal diffusivity is equals conductivity over rho Cp.
Right.
So this is the way. Okay, I got it. Okay.
So
that's why
we measure diffusivity directly. Conductivity is calculated.
Yes. How about a specific heat?
A specific. I mean, we have instruments that can do that. This instrument does not measure specific heat.
Oh, this one doesn't measure a specific heat.
Not that I'm aware of.
Okay. That's why it needs experimental correlation to calculate thermal conductivity. Because I had a question why this machine uses experimental correlation, because analytically thermal diffusivity is equal conductivity over density multiply a specific heat, because it doesn't measure a specific heat. Okay.
Correct.
That's the reason. Nice.
And based on what you just said, is there any range of like mass we need to use?
Yeah, we need to ask application.
So the major considerations for sample prep is thickness more than mass. Right? We're not super concerned about how much your sample weighs. It's more is it thick enough for the energy from the laser to actually be absorbed?
Absorb, yeah.
Or and is it thin enough where that measure or that energy isn't lost in the sample and cannot be detected by the detector at the top? So there's a, in the getting started guide, there's a whole section on sample thickness because it's so important.
Okay. Cool. Thank you.
Okay.
Yeah.
Do you have any other questions for me? Let me just go through quickly. There is some maintenance that should be, done on this instrument. You don't have to pull the lenses out all the time, but it's really good to look at them. So if you look here, this is a really good kind of diagram of the system. Down here is the laser electronics. This is where the laser shines through, right?
Yeah.
This is the furnace. So there's a lens on the top of the laser electronics that can sometimes get dirty. There's a lens on the bottom of the furnace that should be checked occasionally. There's a lens on the top of the furnace that should be checked. These are the two. The ones on the outside of the furnace, that's where the sample is, right? That's the area where there's the most potential for contamination. Yeah, so the top of the furnace and the bottom of the furnace are the ones, and there are instructions on how to get to those. And I think Antonio, he checked all these while he was doing the installation. I'm not sure if you guys were there to see it, but there are instructions here on how to get to those, so you can see that they can get dirty. This is the one on top of the furnace. There's a little lens in there. That should be clear, right? And if you see this, you might have bad signal coming through you, so your shot might look weak, or you might not be getting any reading from your detector. Okay, so something to, you guys don't have to worry about this for a while, but something to think about in the future. This is the one on the bottom of the furnace, and this is the lens that you would need to clean.
Okay.
Those are the two big ones. The rest of them don't get, it's very rare that you'll see any kind of debris settling on those. Okay.
Okay.
So keep in mind that you have this on your desktop. Okay. Right.
Yes. Yes.
Yeah, Josh, I have a question. So,
okay.
When you talk about those data, the curves, what are the abnormal kind of things which we should see in the curve?
Yeah. So let's open up a shot. So I had the comparison up there earlier, and you saw that the rise started happening above the baseline. That's not something we ever want to see. Oh, we already have it running. Oops. So we'll take a good shot and a bad shot to see the difference. So this was from the first. We'll take a couple of them. I'm not sure. This test didn't finish, so take a look at a couple bad shots.
This was the bad one, right?
Yeah, these are bad ones. So you can see that the amplitude is low here, right? So it doesn't look like we were getting as much, and we weren't. We found out that we needed to adjust the positions of the sample holders, right? And you can see that we basically got no rise, so no signal from the detector, right? And also we have a step and a little bit of shine through. So this,
you mean the voltage, right?
Yeah, the voltage. Yeah. So this is very low. And here, let me just open up a good shot so you can see the difference. So you can kind of see the difference here in the scale that we're looking at. We're talking, this is in millivolts, and we're getting about 200 millivolts here. We're only, I don't know, maybe 60.
About
Yeah. So we're getting good signal here, and our rise is not is happening at our baseline rather than halfway up. So these are all signs of, might have something to look at. If you see a shot like this, this is what you're looking for here.
What do you mean by rise in middle way?
Yeah, so if you see here, here, let's zoom in. You can see here that our rise it happens on our baseline. So we have our pulse, right? This is where the laser shoots the sample and is read by the detector, and it comes up on the same baseline. Here, it's very much the opposite, right? Our baseline is here. We have the pulse, and then it's like there's a delay from how the detector is seeing the shot or seeing the energy coming through the sample. So we have to figure something out here. Why are we getting, first of all, why are we getting some of this energy going directly to the detector, not through the sample? This is what this big spike is. And also, why is the detector kind of delayed at starting to see the temperature change? This is what you want to base things on. This is a good shot.
So is a 200 millivolt is a typical value we should look for?
It depends on the sample as well. If you have a very high diffusivity sample, it might be higher. If you have a low diffusivity sample, it might be a little bit lower.
Okay.
But this is the overall shape that you want to see.
Okay, based on what you just said, that means the most important thing we need to check is to see if the rise starts at the baseline, right?
Yes.
About the voltage, we can have like a small range of the voltage, but still have
the overall shape. Yes.
Okay.
Yes. So remember, one of the key things for the diffusivity formula is that half peak time, right? Or peak they call it the peak half time. So if like here's our peak, right?
Yes.
The diffusivity formula takes, so the time it takes for the baseline to get to its peak, it takes half of that. And if the baseline starts way over here, the measurement is or the number that you get out of that is not very good.
Okay.
Okay. Yeah, it might be good to take a screenshot of this and just kind of pop it on your desktop you can get the snipping tool. Oh no, that's not what I want.
Cool. Yeah.
Now you have a reference for the shape of the graph that you want.
Yeah. Thank you. Yeah.
Any other questions for me?
Okay.
reach out to the applications group for your sample prep questions. Okay.
Okay.
And remember that your getting started guide is here. That will
Yeah.
show you how to at least get started on a test. If you get stuck on, where do I click? What do I do here? Things like that, as well as, make sure you prep your sample well, as well as your furnace. It's very important that you evacuate the furnace, especially if you have materials that oxidize, right? So you need to evacuate and then backfill. The instructions are in here. The first few times that you run the instrument, go through this. I know it sounds silly, but read through this before you start it, because you could damage the instrument.
Okay.
Okay.
Do you have any idea about how often we should clean it, or is it based on how many run we did, or is it based on just?
Well, it depends on. So it varies for everybody, right? If you start to see that you're not getting as much, rise that you're used to seeing, you're not seeing that rise in voltage during your shots, might be a good time to look at it.
Okay.
They're not too tough to get to. You take the detector off to see the one on the top. If you see the one on the top is dirty, likely the one on the bottom is dirty too. Okay. So check the top one, and if that's dirty, you should check the bottom as well.
All right. Cool. Thank you.
No problem. All right. If you guys are good with that, I'll end things here. And if you run into any other problems, contact Antonio and I. It looks like Antonio. I don't see Antonio on here anymore.
So Josh, just wondering. So that's all the training, right? From your side.
Yes.
Okay. So I guess from this point on, we can, if we have any operation questions, standard ones, then we contact you, right?
Yeah. So Antonio is your first line there. He's going to be the guy that comes on site if you end up having an issue with the instrument. I can support Antonio. If you want to copy me on your emails to Antonio, that would probably be the best way to do it.
Sure.
Antonio and I will work with you on instrument problems. So if you notice that you're having issues with the instrument itself, the first thing we're going to ask you to do is run the stainless steel, right? Prep and run the stainless steel. We're going to want to see that. If you have sample prep questions or things of that nature, it's best to talk to the applications group.
Okay. Okay. Good. Okay. Thanks.
Problem. Okie dokie, guys. If you run into anything or you're uncomfortable with something, shoot Antonio and I an email, and we'll try and get you squared away. Let me stop the team viewer here.
All right. Cool. Thank you.
And good luck with everything. Remember, don't neglect your getting started guide. That's gonna be your best friend until you get comfortable with it.
Okay.
All right.
All right.
Alrighty. You guys have a good day.
Thank you. You too. Thanks very much.
Yeah. Thank you. Bye-bye.
Bye. You have a good day. Bye.
You want to start?
Yeah, it's finished.